Hello, everybody. Welcome to week 5. We are continuing our energy and change of state. We're focusing in on the heating cooling curve and the amount of energy it actually takes to change the state of energy, to change the state of matter, and to change the temperature. So now you know this, of course, is going to be 0 because this is water. This is 100. Okay? Energy is being added. Well, from here to here, it's raising the temperature. From here to here, it's changing the state. So all of the energy goes to change state. Here, all the energy from this point to this point. So this is really cold ice, 0 degree ice, 0 degree liquid water, melting. 100 degree, here it warmed up. 100 degree liquid, 100 degree gas, and then hotter than 100 degree steam. So energy is needed to raise temperature and to change state. Okay? So there's 2 areas on this graph. There's slants and there's flats. The amount of energy is different, and it's a different equation for flats and slants. So for each of the slants, the formula for change of temperature, that's the slants, used on the slants. Q, which is energy, is equal to the mass times how much the temperature changes times the specific heat. Energy required to raise 1 gram of a substance 1 degree without changing state. So this is how much does it take to melt something. And every substance, every material has a different specific heat. It takes a lot more energy to melt metal than it does to melt butter or melt glass. It would be very high. So this is our equation. Joules, which is the unit of energy, equals grams times delta T, delta being change, times Cp. Cp is specific heat. Now, there's specific heat for water, for ice, and for vapor. So depending on what slant you use, you would use this exact formula, but you would use a different Cp, specific heat, depending if it's the ice. Cp ice would be used here, Cp watt or Cp water, and then Cp vape would be used up here. So how much energy is needed to heat 25 grams of water from 10 to 50? So grams, delta T, Cp, 25 grams of water. My delta T is 40. And because I'm in water, I'm using the 4.184. That's joules per grams degrees Celsius. So it all cancels out, and you end up with joules. Okay? How much energy is released when 100 grams of water cools from 80 to 10? Now, notice our delta T is always positive. Okay? We keep it always positive. It gives us a number of joules, but they would be being released. Okay? So going this way is how much energy is being released. Going this way is how much is being added. So those are the slants. Let's just talk about the flats for a moment. Okay? What's happening on the flat areas of the graph? Basically, you're changing state. Energy is coming in, going out, temperature doesn't change. That's the flat areas. It takes energy to change state without it changing the temperature. You've got the lower flat, which is called the heat of fusion. The upper flat is the heat of vaporization. Okay? Q, energy, equals mass times delta H. One of these, delta H fuse, delta H vape. These are the 2 for them. Okay? So we'll get to that later, but those are the 2 basic equations you need and how to read this graph.